All right, hello and welcome back to our conversation about solution concentration, namely molarity. In our last video, we discussed how we can calculate or find the molarity of a solution by determining the moles of solute and making it a proportion to the liters of solution. So what we're going to do now is we are going to practice using molarity. And when I say using molarity, I mean as a conversion factor. So remember, molarity is equal to moles of solute per liters solution. So when we're talking about a conversion factor, we are using molarity as a known relationship that exists between moles and volume. So let's look at this practice problem here. Always, it's a good idea to think about the goal of your problem. Like, what is it that you're trying to accomplish here? So right off the bat, this problem asks us how many moles of nitric acid. So I know that my overall objective in this problem is to find moles of nitric acid. And if I look at my molarity, where I see moles pop up is here in the numerator, moles of solute. So that's what I want to find. So I'm trying to find my moles, I had better know my molarity of my constant or my solution, my concentration of solution, and the total volume of solution. So let's see if we can't identify any of that information in the problem as given. So how many moles are present in a 50.00 milliliter sample of solution? So right off the bat, I know my volume of solution is 50.00 milliliters. So if I'm trying to find my moles, I'm gonna need my volume of solution. However, I don't want this to be in the milliliter unit. Molarity expresses moles per liter. So I'm gonna have to convert. So you can either write this out and show with a conversion factor that you know there are 1,000 milliliters in 1 liter. Again, this is the exact same as taking 50.00 milliliters and dividing by 1,000 milliliters per liter. Or if you are comfortable with your orders of magnitude conversions like milli, kilo, centi, then you could just move your decimal over. So we could have just moved our decimal over 1, 2, 3 places to the left, because we know that 50 milliliters has to be a small fractional amount of a liter. So doing that decimal place movement, 0. Let's see here, 1, 2, 3. So there has to be another 0 here. So 0, 5, 0, 0, 0, keeping all my sig figs, liters of solution. So I've got my volume of solution. So again, what's my goal? I want moles of my nitric acid. So if I'm going to get these moles, I need information about my solution volume, which I for sure have. And then now I also need to find information about my molarity, the concentration. So let's see here. How many moles of nitric acid are present in a 50.00 sample, 50.00 milliliter sample of 1.2 times 10 to the negative 2 molar HNO3? So I think we've identified our concentration. So our molarity of the solution is equal to 1.20 times 10 to the negative 2. There we go. Molar. Another way we could write this is just moving our decimal over, 0.0120 molar. And if you want to expand it, where it is our unit, you could also rewrite the capital M as moles per liter. Okay, I have officially found my molarity and my liters. So now let's get moles of solute. So remember, molarity itself is going to be the conversion factor, right? This is what's going to allow us to convert a volume to moles or vice versa. So I'm going to start with the quantity that I know. So I'm given a volume, that's my starting place. So I have 0.05000 liters of solution. And then I want to find moles. So I want to cancel out liters and be left with moles. And what do you know? My solution concentration units in molarity already tells me how many moles there are per 1 liter. So in 1 liter of solution, I would expect to find 0.0120 moles of nitric acid. And it is a good idea. Like notice I'm labeling very explicitly what my solution solute solvent is where I can. When we start doing concentration conversions from like one concentration unit to another, it's really easy to get lost in terms of what you're talking about. So it's good practice to not drop these labels that say, oh, I'm talking about moles of this or volume of that. So try to be specific. And if you don't like this visual way of seeing our math, then I'm just going to show it to you as a product. That's what this is. So 0.05000 liters times 0.0120 moles per liter, right? Liter over liter leaves us with moles. If you like the visual method, that's fine. So let's see if we can't get that product. So 0.05000 times 0.0120. When I do this, I get 0.006, 0006, which makes sense, right? Half of 0.012 or 0.012 would be 0.006. And thinking about our unit, this puts us in the mole unit, right? Liters will cancel. So now we have moles of nitric acid. And we're not quite done, right? For one, this mole quantity is pretty small, so we're probably going to want to put it into scientific notation. And then also we need to pay attention to sig figs. Again, like they don't go away. So let's look at our sig figs and the values we were given. So we have 1, 2, 3, 4 sig figs in my volume. And we are assuming that this molarity is something that was determined in the lab, right? It's not something that's perfectly known or known with a really high degree of precision, like a molar mass, or something like we know that there's 1,000 of millis in a liter or something like that. So I'm going to also count the sig figs in my concentration. So I had 1, 2, 3, 4 sig figs in my volume, but I am limited to only 3 total sig figs in my concentration. So I need to express this so it has 3 sig figs, and I also want it to be in scientific notation. So 6.00 times 10, let's do our little movement here. So 1, 2, 3, 4. That's what will put my decimal to the right of the 6. So that is times 10 to the -4 moles nitric acid. So we have met our goal. We've used molarity as a conversion factor to find moles from volume. Okay. Let's do this, but in reverse. So again, we're using molarity as a conversion factor. So I'm just going to write my definition of molarity. This is moles of solute per liters of solution. And then we're going to start by identifying our goal. So reading our problem, what concentration of nitric acid is needed? So what concentration of nitric acid is needed? So we know that we're going to try to find a molarity. So goal, we want the molarity. And let's keep reading. What concentration of nitric acid is needed to give 25 mils of solution that contains that many moles? And I have italicized something here of nitrate ion. So I don't want my solute to be just nitric acid. My solute here is specifically the nitrate polyatomic ion. So how is that going to change things? Let's work through this bit by bit. So I want my molarity, and if I want molarity, that means that I need to find my volume of solution. So reading my problem, what concentration of nitric acid is needed to give 25.00 mils of solution? So I have some information about that. I have 25.00 milliliters of HNO3 solution. And we are going to need to put this in liters. So we could do our conversion factor where we say that for every 1 liter, that will contain 1,000 milliliters. So we're dividing by 1,000 here. We are moving our decimal place over 3 places to the left. This is 0.02500, retaining our original significant figures, liters of HNO3 solution. So we have our liters of solution. Now, moles of solute, specifically the nitrate ion. So let's take a look at what this problem is saying. What concentration of nitric acid? So we are asked, like, how much nitric acid is needed so that we have a nitric acid solution that contains this number of moles of nitrate ion. So what we need to ask ourselves here is how does the number of moles of nitric acid in this solution relate to the number of moles of nitrate ion? So we have to think about what's actually in the beaker when we dissolve nitric acid in solution. So you might remember this from Gen Chem 1. Nitric acid is a strong acid. And by definition, if you're a strong acid, you are going to have a full dissociation of ions, just like something like sodium chloride would. So let's write out this dissociation. I think that's helpful. So here, full dissociation of ions. Let's write the dissociation equation. So if I take nitric acid and I dissolve it in H2O, then I'm going to have in solution H plus split up from NO3 minus, because I'm recognizing nitrate as the polyatomic ion. So the dissociation or the severing of that ionic bond is happening here. So why was this important information to know? Like, what was this a good reminder of? So again, this question that we're asking ourselves is, how does the number of moles of nitric acid relate to the number of moles of nitrate? So this is really a stoichiometry question. This is asking us if we were to look at the ratio of nitric acid to nitrate ion, what would that ratio be? In other words, when I dissolve 1 right? That's what's implied with nothing drawn out here. So when I dissolve one nitric acid molecule in solution, I generate one nitrate ion. Scaling that up to be a mole ratio, I can say for every 1 mole of nitric acid, that's equal to 1 mole of nitrate found in my beaker. Because for every nitric acid that we put into solution, every nitric acid molecule that we dissolve, each one's going to split up to put H plus and NO3 minus into the beaker. So how can we use this to get moles of nitrate? So let's see here. If we know that the moles of HNO3 is equal to the moles of nitrate, then really this problem is saying that the nitrate moles is equal to the nitric acid moles, and we don't need to like worry about whether we're thinking about this dissociation. If this was something else, like if it was well, maybe not nitric acid, but something where the mole ratio wasn't 1-to-1, but maybe 1-to-3, we would have to take that into account. But here, since everything is 1-to-1 in our dissociation stoichiometry, I can figure out my moles of nitrate ion. So I've got 4.012 times 10 to the negative 4 moles of nitrate ion, which means because of this 1-to-1 ratio, I have 4.012 times 10 to the negative 4 moles of nitric acid. Because again, that's what our solution is talking about. It is a nitric acid solution. So now let's find our molarity. Molarity is equal to our moles. 4.012 times 10 to the negative 4 moles of HNO3 solution over the volume in liters, 0.02500 liters. So let's do that math. So thinking about this instead of scientific notation, so that's 0.0004012 moles divided by 0.02500 liters. Unrounded, I get 0.016048 molar. And now we need to do our sig fig analysis. So I had 1, 2, 3, 4 significant figures in my volume, and then 1, 2, 3, 4 significant figures in my moles, which means I need to retain 1, 2, 3, 4 significant figures in my molarity. So I'm going to round that last digit up because its following digit is greater than 5. 0.01605 molar nitric acid solution is required to ensure we have the quantity of nitrate ions desired in solution. Okay, so if we're talking about ionic compounds, especially ones that are very, very soluble, and we'll elaborate on solubility a little bit later in this course, you want to make sure that you're checking your, like, what's in the beaker perspective. So if I'm mentioning nitrate ion, that should be a clue for you that you need to look at what kind of ions and in what proportion are put into solution. All right. In our next video, we will do a little bit more practice, and then we will talk about solution density. So we've practiced with concentration, one of the prime intensive properties we use to talk about or describe or characterize solutions. And the next one we have is density.